So multiplexer, what is a multiplexer? So it is a digital circuit. It is a digital circuit which selects one of the n data inputs. It selects one of the n data inputs and passes or routes it to the output and passes or routes to the output. So we will have this multiplexer is one of the important thing that we will come across or that is most widely used. So all are most widely used, but it is most widely used. Why? Because so multiplexer, what it is doing, it is selects one of the n data inputs and passes to the output. So for example, it is the most practical example is in the telephone example. So actually, while connecting from one city to another city, or from one place to another place. So for example, in one city we have some 100 customers. In another city, for example, you take the same 100 or more than 100 customers, right? So we cannot have a line from how many customers in one city to those many customers present in the another city, right? We cannot have those many lines. So what it does means, so from one city to another city will be connected by only few lines. It will be connected by the or one line. In fact, one line, but it will have a large bandwidth. So what it does means multiplexer, it selects one of the, so for example, out of 100, some 10 people are calling to another 10 people which are in the another city. So what multiplexer does means, so out of these 10 people, and next thing, what is the important thing means, out of these 10 people will not talk continuously, right? All the 10 people will not talk continuously. There will be in between breaks. So if some first person is speaking, then that voice will go through, the second person has to reply back. So while the second person in the another city, while he is replying back, the first person in the first city will not talk. He will listen to whatever that person is speaking in the another city. So so the talk, whichever is going, it is not continuously. So there will be a break in between talks. So what this multiplexer does means, so whenever first person is speaking, it will take that voice and it will carry through this line. So only one line we will have. So I am saying roughly. So it may not be exactly always the same. So we'll have all 10 persons are connected to this line. So what multiplexer do means, so it will give out of one or some 60 seconds will be there, right? In 1 minute we will have 60 seconds. So for all the 10 customers, 6 seconds will be assigned. 6 seconds will be assigned. So whatever the first person, if he is speaking, so whatever he is conveying, that will be connected through this line. Second 6 seconds, it will be connected to the second person, like this. So all the persons will be connected to this line. So that is what, this is a rough idea or where we will use the multiplexer. So it's all our data or some information they are going to convey. So what multiplexer does means, it will select one of the n data inputs and passes to the output. Passes means through this line. So how we will select the, out of these 10 lines, how we will select one person or one voice means, that is based on the selection inputs. How we will select, how we will choose the input, which input need to be passed through this line. So it depends on the selection lines. So there will be relation between number of inputs and the selection lines. Number of inputs we can take it as n, and the number of selection lines in general m. These may not be always the same. You can use any, but these are in general that are used in most of the textbooks. Selection line. So obviously you see number of inputs will be more and selection lines will be less. So always n will be more. The number of input lines will be more and selection lines will be less. So a multiplexer, in short, it is also called as mux. In short, it is also called as mux. So the multiplexer, in short, it is called mux, or it is also called as a data selector, because it is most of the times it is used for selecting the data. One of the out of the many data inputs that we have, it is used for selecting the one of the data inputs. So that is why it is also called as the data selector. So this is how the multiplexer will look like. So these are the data inputs. These are the data inputs. So how many? So this is D0, D1, D2 and so on, Dn minus 1. So n input lines will have, n input lines, total n input lines will have, and m selection inputs. So these are the selection inputs. So how many selection inputs means m selection inputs, S0, S1 up to Sm minus 1, and this is the output. Only one output. Only one output will have. So we'll have n input lines. We'll have n input lines and m selection inputs. Always the input lines are more. Input lines are more. So we'll have one more input apart from the data input. The other input is the enable input. The other input is the enable E input. Here E is nothing but the enable input. So this enable input, as it from the name itself we can guess. So it enables. So in general it can be act to low or act to high. The enable input can be act to low or act to high. Act to high. This enable input can be act to low or act to high. Act to low means, so act to low means, so if that input is 0, then only this multiplexer will operate. Then only it will operate. So if that is the case, then it is called act to low enable input. So there are ICs. Act to high. Act to high means we should give that input as 1. So only if E is equal to, for act to high case we should give E is equal to 1. For act to low case we should give E is equal to 0. So for act to high case we should give E is equal to 1. Then only it will operate. Otherwise it will not operate. So this is the general block diagram. So this is also represented like in this way. So in this way also it will be represented. So several input lines will have, and selection lines also will have, one output line will have. So this is the output and these are the input lines, inputs, and these are the selection inputs. So this is also represented. So both are equal symbols. So but this is more appropriate symbol. So because we will have many inputs, but we will have only one output. So that is we can observe from this thing, from this representation, block diagram representation. So that it is more appropriate. It is also correct if you draw in this way also it is correct. But this is also, this one is the more appropriate one. Here another important thing that you should observe is input lines will be more. N is always greater than M. Selection inputs will be less than the actual input line. So we will see what is the relation between selection inputs and actual data input. And another important thing is enable input. This enable input can be act to low or act to high. So if it is act to low case, then we should give always E is equal to 0. If it is act to high, we should always give E is equal to 1. So we will see what is the purpose of this enable input in next thing. So this also useful for realizing the any combinational logic, right? So first we will see 2:1 multiplexer. So here what this thing is representing. So we'll see. So 2:1 means 2:1 means, so we'll have two data lines and one selection output and one output. So here this thing indicates the number of inputs. So this one is always the output. So this indicates the number of input and this indicates the number of output. So number of inputs are 2. So for example, this is I0, this is I1. So we'll have selection lines here. How many lines are required in order to select two inputs? In order to select two inputs, we require only one selection line, and this is the output. So these are the inputs. And this is the selection input. So for selecting the two inputs, we require only one selection input, only one output. So here, so always multiplexer we will represent in this way. So what is this means? It is 2 power n is to 1 mux. So where n is the number of inputs, so n is the number of inputs. So if number of inputs, so if n is equal to 1, 2 power 2 is to, always we will have in this way. This is m, 2 power m is to 1. So 2:1 or 4:1. So this is m. 8:1. 8:1, 16:1, 32:1, right? So now can anyone tell what is the relationship between the selection inputs and the actual data inputs? So these are the data inputs and this is the selection input. So this is selection input will represent with M and these are the inputs. So what is the relation? Data inputs. So data inputs are n. So n is equal to 2 power m. N is equal to 2 power m. So that is what represented. So these are the number of inputs. 2:1 mix. 1 mux means it will have 2 inputs, 1 output. 4:1 mix means it will have 4 input lines. So this other way, this we can write it as m. So for n input, what is the number of selection lines we require? It is log n to the base 2, or this is the other relation. The number of inputs and the number of selection line required is given by this relation. So output, here the output is represented. So output, how we can represent in terms of data inputs and selection input means, so how this is connected or how this is related means, so for example, we'll have as here 2:1 max. So we'll have only one selection input. So what is the corresponding possible values for the selection input? Either it can take 0 or it can take 1, right? So what it will do means, if selection input is 0, so it will select I0. So if selection input is 1, it will select I1. So how the output is represented, or what is the relationship between output and data inputs and selection input means? So what we are saying, if selection input is 0, it will select the data line I0. So S is equal to 0, how will represent S prime or S bar, right? So if S selection input is 0, it will select I0. So I0, right? And then if S is equal to 1, it selects the I1. It selects the data input I1. So S is equal to 1 means simply S. So I1. So this is the relationship, the output. This is the relationship between output and the data inputs and the selection line. So in order to realize this, how many gates we require? 2 AND gates and 1 OR gate are required. 2 AND gates, right? 2 AND gates and 1 OR gate is required. 2 AND gates and 1 OR gate is required. 1 OR gate is required. So this is the output, and here we'll have the data input I0, and here we'll have data input I1, and we'll have the selection line. So to select I0, so the selection input we need to pass through inverter, right? And to select I1 we need to pass through straight away. So if S is equal to 0, for example, if S is equal to 0, so if one of the input to the AND gate is 0, what is the output? This output will become 0. So what about this? So here we will have, because S is equal to 0, this is passed through the inverter, so here we will get 1. So whatever is, if I0 is equal to 0, we will get here 0. If I0 is equal to 1, here we will get 1. So if S is equal to 0, so here we will get I0 and here 0. So the output of this OR gate is simply I0. So if that is not the case, if S is equal to 1, for example, if S is equal to 1, if S is equal to 1, if S is equal to 1, so then what will happen? If S is equal to 1, so here what we will get? Here we will get 0, so then this AND gate will be disabled. So S we are connecting directly to this AND gate. So whatever I1 is having, so that value will come here. So the output will get I1. So how we can represent this in the form of a truth table? In the form of a truth table, how we can represent? So we can have one output, right? And based on the selection line, if S is equal to 0, what is the output we are having? We are having I0. So if S is equal to 1, we are having I1. So this is the truth table. Representation of a 2 cross 1 mux. So we'll have only one selection line. So that S value can be 0 or 1. So what is the output? If S is equal to 0, the output, whatever I0 may be having 0 or 1 value. So if it is having 0, we will get 0. If it is having 1, we will get 1. So if S is equal to, if selection input is 1, the output will be simply I1. So this is the truth table, and this is the inside the mux. We will have this type of block diagram. So this type of circuit diagram. So inside this mux block diagram, we will have this type of circuit. So here what we have seen. So for a 2 cross 1 mux, the number of input lines are 2. So whenever we are representing in this way, so this indicates the number of inputs and this indicates the output. And what is the relationship between? So M is nothing but the number of selection inputs, and N is nothing but the number of data inputs. M is equal to log n to the base 2, or N is equal to 2 power M. So if M is equal to 1, we will have 2 data inputs. So if M is equal to 2, we will have number of data inputs are 4. Right? So this is how we will represent the output. The relationship between output and input data lines and the number of selection input is nothing but S bar I0 plus S into I1, and this is how we will have always. And here also we will have 2-level realization. First level it is AND gate, and the second level it is OR gate. So this is the about 2 cross 1 line. So next, 4 cross 1 multiplexer. So here 4 indicates the number of inputs. So how many selection lines we will have? M is equal to log 4 to the base 2. So it is nothing but 2. So for a 4:1 multiplexer, for a 4:1 multiplexer, we will have two selection lines, S0 and S1, S0 and S1, right? So what are for two inputs? For two inputs, how many possible combinations will have? 0, 0, 0, 1, 1, 0, 1, 1. So what is the corresponding decimal equivalent? It is 0, 1, 2, and this is 3. So what is the output? What is the output? So for 0, 0, if selection inputs are 0, 0, we will have I0 as the data. Output is nothing but I0. If it is 0, 1, we will have I1. If it is 1, 0, it is I2. If it is 1, 1, it is I3. So sometimes instead of I0, they may use D0, D1, D2 like that also. You can use anything. So this is how the internal block diagram of a 4:1 multiplexer will look like. 4:1 multiplexer will look like. So how many inputs will we have? 4 inputs. 4 inputs we'll have. So 4 inputs we have, and 2 selection inputs. 2 selection inputs we have. 2 selection inputs we have, and 1 output. 1 output. So if it is 0, 0, if selection inputs are 0, 0, if both are 0, 0, you see how. So this is the I0 or the first AND gate, second AND gate, third AND gate, fourth AND gate. So which lines you have, you see? So S1 is connected through an inverter, and similarly you see, so this line is connected through S0. Through S0 passed through inverter. So whenever S1 and S0 both are 0, 0, both are 0, 0. So this gate will be enabled because they are connected through the inverter. You see other gate, they are directly connected. So you see the second gate, at least one of them are directly connected. You see for second AND gate, so this is the connection we have. This is the, so S0 is directly connected. So even one of the input is 0, so the AND gate will be disabled. AND gate will be disabled. So for 0, 0, only the first AND gate is enabled. The remaining AND gates are disabled. So for 0, 0, if selection inputs are 0, 0, I0 will be passed as it is here. So if S0, S1 are 0, 1, 0, 1, you see for second AND gate how they are connected. So second, so through S1, it is connected through the inverter. You see, you cross check here. S1 is connected through the inverter. Whereas S0 is directly connected to the second gate. S1 is connected through the inverter. S0 is directly connected. So for 0, 1, only the second gate is enabled, remaining will be disabled. So whenever this is enabled, I1 will be passed as it is. So for 1, 0 combination, this gate, third gate will be enabled. For 1, 1 combination, this gate will be enabled. I3 will be passed as it is. We cross check. S1 is connected directly. And S0 is also connected directly. So whenever S1 and S0 both are ones, I3 will be passed as it is. So inside a 4:1 multiplexer, we will have this type of diagram. This type of logic circuit is there inside a 4:1 multiplexer. Like this, any multiplexer will have in the first level AND gates, and the second level will have OR gate. In the first level we will have AND gates, and the second level we will have OR gate. So how many AND gates we will have depends on how many inputs we will have. If we have 8:1 mux, so inside the multiplexer circuit we will have 8 AND gates. 8 AND gates will be there. 8 AND gates will be there. So the number of AND gates inside the multiplexer will be equal to the number of inputs it will have. So how we can write the output in terms of inputs and selection input. So output I0 will be selected when both S1 and S0 are 0, 0. So it is S1 bar, S0 bar and I0. And I1 is selected I1 is selected when S1 is 0. So S1 bar and S0 is 1. So it is simply S0. So I1. And next I2 will be selected. I2 will be selected when S1 is 1 and S0 is 0. S0 is 0. S1, S0 bar, I2. And I3 is selected when both S1 and S0 are 1, 1. So it is S1, S0 and I3. So this is the relationship between the output. This is the relationship between the output and the selection lines and the input. So this is how we will write the output, selection lines and input, right? So now we will see what is the advantage of using multiplexer. So how we can implement a given Boolean function. How we can implement a given Boolean function by using the multiplexer. So what is the size we need to select? What is the size of the multiplexer we need to select? Those things we will see now. So by using the multiplexer, we can realize a given Boolean function more efficiently. Or what are the advantages? What are the advantages that we will have if we implement a given Boolean function by using the multiplexer? By using the multiplexer, what is the advantage if we implement by using the multiplexer? Simplification is not required. So what is the advantage of implementing a given Boolean function by using the multiplexer means simplification is not required. Simplification is not required. So that is the first advantage. We used to simplify by using K-maps, right? Whenever we want to implement the given Boolean function, so we used to simplify by using K-map. So if we implement given Boolean function by using the multiplexer, we need not to simplify. Simplification is not required. So as simplification is not required, we can very easily implement the way of implementing the given Boolean function by multiplexer is easier. So these are the advantages. So why it is more efficient, we will see. So how to select which multiplexer, what is the size of the multiplexer that we require in order to implement a given Boolean function. So you see the minimum size or the size required will depend on the number of inputs. So here we have three variables. So the size that is required or the number of input lines we can have is 2 power 3, right? So the number of input lines for 3 variable case, maximum number of possible cases are 8. So that is why. So how it is decided? 2 power 3. So here 3 is the number of variables. So this we can select as the selection inputs. Selection input. So the given Boolean function is represented in terms of minterms, right? It is represented in terms of minterms. So for 1, 2, 6, 7, the output will be 1. The output will be 1. For remaining combination, what are the remaining combinations that we have? those are 0, right? 3, 4, 5. So for these combinations, the output will be 0. So for these combination, we have to connect the input as 1. For these combinations, we have to connect the input as 0. So that we will see in the form of truth table and then the mux implementation. So we have XYZ, right? XYZ. So the total possibilities are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So write the corresponding decimal equivalent 0, 1, 2, 3, 4, 5, 6, 7. So the Boolean function is having the min terms 1, 2, 6, 7. So for those combinations only, we'll have the output as 1. So 1, 2, 6, 7. So for remaining combinations, we have we should have the output as 0. For remaining combination, the output should be 0. So what is the mux size that we required? We require an 8:1 mux. We require an 8:1 mux. 8:1 mux. 8:1 mux. So 0, 1, 2, 3, 4, 5, 6, 7. 5, 6, 7, and selection lines we will have. Selection lines S0, S1, S2. 3 selection lines we have, right? So the input variables we will connect here. So this is the, so in which way we have to connect the input variable. So that plays important role. So for LSB we have to connect S0. So simply if we reverse the order, the output will completely change. So for S0 to connect to S0 and MSB we need to connect to S2. So otherwise it will be completely opposite. So here what we need to connect to this selection or so data input means, so wherever we have the min terms, so for those we need to connect 1, for remaining we need to connect 0. So 1, 2 and 6 and 7. So for remaining we need to connect zeros. For remaining thing we need to connect the zeros. So in order to realize the given Boolean function by the multiplexer, this is the one procedure by using 8x1 mux. 8:1, or in fact it is also represented 8x1 mux also. So the important thing is, to the LSB we need to connect to S0 and MSB we need to connect to S2. So why it is called more efficient method of implementing a given Boolean function? Why it is called more efficient method? So for this given Boolean function, we have used 8x1 mux. So we can implement the same. By lower order mux also. 4:1 mux also we can implement. By using the 4:1 mux also we can realize this Boolean function. So how it is means we will see now. So what are the min terms that are given? So 1, 2, 6, 7. 1, 2, 6, 7, right? 0, 1, 2, 3, 4, 5, 6, 7. Right? So now remaining For remaining minterms, for remaining combination, the output should be 0. Now we say how we can realize the same by using 4:1 mux. How we can realize the same by using 4:1 mux. So 4:1 mux means the number of inputs to that mux are 4. But here we have total 8 possible combinations. So 8 possible combinations. But how to select only or how to realize by using 4:1? So how means, so out of the 3 variables, so we have to relate the LSB, we have to relate the LSB with output. We have to relate the LSB with respect to output. We have to relate the LSB, or we have to find the relationship between the output and LSB. So if you observe X and Y values for 2 consecutive rows, they are same. For 2 consecutive rows, they are same. 0, 0, 0, 1, 1, 0, 1, 1, right? So 0, 0, it is nothing but I0. For 0, 1, it is nothing but I1. And for 1, 0, it is I2. For 1, 1, it is I3. Now observe the relationship between the output and Z. So for these 2 rows, for 0 here also, for both the cases we have 0, 0. Now observe the relationship between output and Z. You write the relationship between output and Z. What is the relation? If Z is equal to 0, output is also 0. If Z is equal to 1, output is also 1. That means the output for this combination of 0, 0, the output is same as the third variable or the LSB variable Z. Right? So for 0, 0, for X and Y 0, 0 combination, the output is simply following the third variable Z. So that is what we have written, output is equal to Z. Next, for 0, 1 combination. For 0, 1 combination, you observe the output is 1 if Z is equal to 0. The output is 0 if Z is equal to 1. That means there is an inversion relationship. For these 2 rows, output is nothing but simply Z prime or Z bar, right? If Z is equal to 0, output is 1, and if Z is equal to 1, the output is 0. Next, 1, 0 combination. For 1, 0 row, you see, whatever may be the Z value, for these 2 rows, output is simply 0. Next, for these last 2 rows, X and Y values are same. Irrespective of the Z value, whether it is 0 or 1, the output for these 2 rows, it is simply 1. So by making the relation or by finding the relationship between output and the LSB variable, we can implement efficiently the given Boolean function by smaller size mux. So how we can implement means we will see now by using the 4:1 mux. So 4:1 mux means how many selection lines we will have? 2 selection lines, S1, S0. Again, for S1 we need to connect X. For S0 we need to connect Y, right? And we'll have 4 inputs. So what are those? I0, I1, I2, and I3, and 1 output. So this is the 4:1 mux. So for I0, what we need to connect? For I0, we need to connect the Z variable. Right? So for I1, we need to connect Z bar. So that means we need to pass through an inverter, this Z, and then we need to connect to I1. So for I2, we need to connect simply 0. For I2, we need to simply connect 0. For I3, simply connect 1. So you see, so if XYZ values are all 0, 0, XYZ values all are 0, 0. XY 0, 0 means it will select I naught. It will select I naught. So what is the Z value here? We are having 0. So simply we are having 0. So what is the output? We will get 0, right? So that is here also in truth table you see for 0 0 0 the output should be 0. So here we are getting the same thing. So next 0 0 1. So for 0 0 still it will select I0. It will select I0. So that means this one. But what is the value that is passing through this? It is 1 is passing. It will select still I naught. For 0 0 it will select still I naught. For now Z value is 1, right? Now Z value is 1. So instead of 0 now we will get the output as 1. The output as 1. So in this way, next if it is 0 1, if it is 0 1 it will select I1. It will select I1, right? Will select I1. So now you see Z value. So Z is equal to 0. Z is equal to 0. So here we are having 0 means, so here we will have 1. So output for 0 1, for 0 1 will get the output as 1. Next for one same 0 1 only, it will select I1 now, but Z is equal to 1. If it is Z is equal to 1 means, so here we will get 0. Now output will be 0. So in this way, by using 4:1 mux. So earlier we have seen 8:1 mux. So this is what it is more efficient means the same Boolean function we can realize by lower order mux. We can realize by using the lower order mux. Similarly, we can implement the same function with 2:1 mux also. With 2:1 mux also. But when we are implementing 2:1 mux, we require AND gates, other gates also we require. Other gates also require. You see, when we are implementing with 8:1 mux, 8:1 mux, simply we have connected 0 1. We have connected to the data input 0 1. When we have connected by using 4:1 mux, we have connected only the NOT inverter gate. So if we use 2:1 mux, we may require other gates also, AND gates and OR gates also may be required. So this is how we can implement a given Boolean function by using the multiplexer. So here we doesn't require any simplification. We doesn't require any simplification. So it is more easier way of implementing a given Boolean function by multiplexer, right? So is it clear? I hope it is clear to everyone, right?
If you like the video, please share, like and subscribe. Hit the bell icon to get latest video updates.